Thanks for the introduction. Good morning, everyone. Thanks for coming to this session. This is Chao Zhang from UIC. I'm a fourth-year PhD student at UIC. And today I'm going to present our work on using social media to detect local events. This is a joint work with my colleagues from UIC and also some researchers from US Army Research Lab. So in today's world, everyone and everything is getting increasingly connected. The meals we have, the flights we take, or the concerts we attend, pretty much for every activity we do in our daily life, we can share it with our friends in online platforms. For example, Twitter, Instagram, Snapchat, Facebook, and many others. And such activity sharing behaviors result in the so-called geo-tagged social media. In a geo-tagged social media, you not only have the text message, you also have the location and time information about your current activity. Here's an example. Here's a geotagged tweet published by some user. You can see there is location information, and also there is time information and text information. So we can understand not only where the user is, but also what he's doing and when is he having the activity. And the amount of such geotagged social media is very huge on different platforms. For example, on Foursquare, there are more than 8 million check-ins every day published, and on Twitter, there are more than 10 million geotagged tweets. On Instagram, there are more than 20 million geotagged photos. So you can imagine such millions of geotagged social media posts, they are actually a result of so-called human sensing, which means millions of human sensors, they go to different areas in the city, and they explore the different activities in the area and share their activities online. And our goal is to detect the local events from the social media streams. A so-called local event is an unusual activity that's burst in a local area and a specific time duration, while engaging a very large number of participants. For example, a local event could be a concert, could be a football game, could be a protest, or any other interesting and unusual activities. So more formally, our input includes a continuous geotagged tweet stream, which we call D, and also a query window, which we will call Q. And the task here is to find all the local events falling inside this query window queue. Also, when the query window shifts, we want to update the event list when new instances from the stream arrive. There are a few previous methods to local event detection. They can be divided into two categories. The first is the feature-based methods. The main idea is that given the social media stream, we first find the bursty keywords using signal processing techniques like wavelength transform. And after we find those bursty keywords, we try to cluster them into meaningful candidate events based on their spatial and temporal distributions. And after that, we can come up with some measures to quantify the burstiness degree of each candidate event, and we select the top K bursty candidates. This is a feature-based method. And second method is the document-based method. So for document-based method, it first class the tweets into meaningful geo-topic clusters. The intuition here is that, let's suppose there is, for example, a protest happening in the Fifth Avenue, then many participants of this protest may publish tweets about this protest. And those tweets are geographically close because they are all around the Fifth Avenue, and also they are talking about the same protest, so are semantically relevant. So they form a geotopic cluster. After finding those geotopic clusters, then document-based methods try to measure the burstiness of different clusters and then finally identify the top K bursty clusters. But there are two drawbacks that the existing methods do not address very well. The first is that the quality of the candidates' events are actually quite limited. So in previous studies, they mostly use the bag of words to represent the text message, and then they try to come up with, for example, the call sign similarity in the vector space to measure the similarity between messages and find the geotopic clusters. Since the social media posts are usually very short, they usually suffer from the short text sparsity. For example, if a user say Kobe and another say KB, using the bag of words representation, the correlation between different keywords may not be captured very well. And we need to come up with a better way to capture the short text semantics. The second drawback is that the top K selection process is actually very rigid and not optimal. For top case selection, they usually need a manually designed ranking function for quantify the bursting list degree of different candidates. But even if we have such a ranking function, the top case selection is not very flexible. You can imagine some query windows, they may contain more than k events inside that time duration, and some may have no events at all. But top case selection will return k events for any query window. That's not very flexible. So that's why we propose our method called TrioVecEvent. So there are three major components in TrioVecEvent. The first one is that we generate the multimodal embeddings of location, time, and the text. We map different data types into the same latent space to capture their correlations. If two units are very similar or correlated with each other, then their embeddings will be close in the embedded space. For example, around the JFK airport area, maybe you observed flight or airport or similar keywords in this area. Then the keyword flight and the area JFK, they'll have close embeddings in the latent space. So such embeddings will help us to capture the correlations not only between keywords, but also between words and the location and the time. Once we have those multimodal embeddings, we'll use the embedding to find geo-topic clusters as our candidate events. Because the embeddings capture the correlations between different units, then we will use them to find very coherent geo-topic clusters. For example, maybe one cluster corresponds to the shopping activity around Fifth Avenue, or some protest around another location. Then we can consider those those clusters as candidate events. But as I mentioned, not every geo-topic cluster is a true event. For example, in the Fifth Avenue, pretty much every day you'll observe a cluster of shopping-related tweets because so many people visit the location and have the shopping-related activity. So in the third step, we'll extract features for the candidate events, and we'll train a classifier to determine whether each candidate event is a true event or not. That's the three major components in our method. First, embedding, and then find the clusters as candidates, and finally, train a classifier to determine whether a cluster is a true event or not. Okay. So now let's look at the details of each module. So the multimodal embedding is actually a simple extension of the existing Seibao model. The goal here is that we want to embed all the location, time, and keywords into the same latent space to preserve their correlation. So we define an objective function that tries to reconstruct each attribute I inside a document D. Suppose we have a document D, we first mark off the attribute I, and then we try to use the rest attributes in D to define its generative probability of attribute I based on softmax function. And the similarity between attribute I and the rest attributes is just a simple inner product. And in this way, we'll be able to use the Geo-Tagged tweets to learn the embeddings of different units as our multimodal embedding. Okay, so once we have the embedding, then for every tweet D, we describe it with two-dimensional location L, denoting its GPS coordinates, and then also a text embedding X, which is a fixed size embedding vector. And our goal is that we want to find all the geo-topic clusters in the query window, so that the tweets in the same cluster, they are geographically close and they are semantically similar. To find geo-topic clusters, we design a Bayesian mixture model. You can see from this graphic model, we actually define a generative process of all the tweets in this query window. So the graphic model may seem complicated at first glance, but if you want to understand it, the most important two parts are here. First, for every tweet D, we have a latent variable ZD to indicate its cluster membership. Once we have this cluster, we define the generative process of the location using a Gaussian distribution. And also, for the text embedding, we use a Vomitous Fisher distribution to generate its text embedding. Perhaps not everyone is familiar with Vomitous Fisher distribution, so I'd like to introduce more about this part. because it's not a very common distribution. In the VMF distribution, there are two major parameters. The first is the mean direction of the cluster on the unit sphere, and the second is the concentration of the points around the mean direction. The intuition here of VMF is that the cosine similarity can capture the similarity between the text embeddings, and then they can naturally lead to the choice of using VMF for finding clusters on the unit sphere. Because if we use cosine similarity to measure the similarity, then the magnitude of the embedding vectors do not count very much. We only care about direction and also the relative concentration around the direction. For example, here on the right part of this slide, I show example of 4 clusters. Maybe one cluster corresponds to concert, another corresponds to game, and the rest corresponds to protest and shopping. Then for every cluster, it has the semantic focus as the mean direction of the VMF distribution. And then around this semantic focus, there are relevant points that fall around this mean direction. So based on our Bayesian mixture model, then we can use MCMC to infer the parameters. We can infer the cluster membership of every tweet in the query window, and also we can infer the distribution of every cluster. Another part of the clustering is that suppose we are dealing with the streaming data. When new data arrives, we want to update our cluster results incrementally. So we propose a very simple but effective online updating strategy. Suppose the query window shifts from queue to another query window. Then we remove the outdated tweets. And then for the new tweets, we sample their cluster memberships using MCMC. And also to avoid the accumulation of error, we periodically recompute the clustering results. In this way, we are actually achieving a balance between effectiveness and efficiency. Okay, so that's all about the candidate generation step. Now that we have the geo-topic clusters in the query window as the candidate events, our last module is the candidate event filtering that tries to determine whether every geo-topic cluster is a local event or not. We cast the candidate filtering step as a binary classification problem, which means we want to extract features for every candidate event and train a classifier to determine whether it's true or false. We have proposed a set of features. The first set is the spatial and temporal accuracies. The intuition is, for example, on the Fifth Avenue, maybe the common activities are shopping related, but if there is a protest occurring around the Fifth Avenue, then this protest activity is actually very spatial and temporal unsure. And the second is the spatial and temporal concentration, which measures how concentrated the tweets in the same cluster are spatially and temporally. And the third one is the semantic concentration, which means whether the tweets in the same cluster, they are talking about the same semantic focus. And finally is the burstiness degree. In our experiments, we use 2 data sets. The first is the Geo-Tagged tweets in Los Angeles during a 4-month period. And the second is the Geo-Tagged tweets in New York during the same time period. For pre-processing, we use an existing NLP tool to extract the entities and non-phrases from the raw tweet messages. Because we find that the raw tweet messages are actually very noisy. So after extracting the entities and the non-phrases, we actually preserve the most important indicators of the events. For evaluation, we randomly generate 100 query windows, and then we detect the events in those query windows, and we upload the results onto Crowdflower, which is crowdsourcing platforms, and ask the workers to judge whether the retrieved local events are valid or not. So before I show the numbers, I'd like to first show you some examples of the multimodal embeddings. So what we do here is that on each of the 2 data sets, we use our embedding algorithm to train the multimodal embedding. Then we have the representations for location, time, and text, and we do some similarity search. For example, in this figure, the leftmost example is a query keyword beach. And for this query keyword, we retrieve the top 10 most similar locations on each data site. You can see the top 10 locations, they all fall around the coastline in LA and New York, which shows that the embedding can indeed capture the correlations between location and keywords. And also we have shown the retrieval results for the query around the airport, LAX airport, and the JFK airport. Again, you can see the when retrieving using this location, the top 10 keywords are like LAX, International, United, TSA, those stuff. So they are very related to the airport area. So you can see the embeddings can indeed capture the correlations between keywords and also show you what are the typical activities around different locations. And in these slides, I show you some example results we detected on LA. The first event is actually a protest rally at the LAPD headquarters. On the left part, we can show the location of the tweets in this cluster. They are very concentrated. They are all around the LAPD headquarters. And on the right part, you can see the text messages of those tweets, like standing for justice, and they are very related to this protest as well. It's interesting to see that even if tweets use different keywords to describe the same protest event, we can still cluster them together as the candidate event. And the second local event is Katy Perry's concert at the Staples Center. Again, we can see the location is very concentrated, and also the text messages are very semantically relevant. Here are more examples on the New York data side. We can find local events like the Hoboken Music and Art Festival, and also the Knicks basketball game at the Madison Square Garden. So for effectiveness comparison, we compare our method with several existing methods. The first is the event tweet method, which is published in 2013 VLDB. This is a feature-based local event detection method. And second is the GeoBurst method, published in 2016. And also an extension of the GeoBurst method, GeoBurst Plus. The difference between GeoBurst and GeoBurst Plus is that when filtering the candidates, GeoBurst Plus uses a classification, not the top case selection. So from this table, we can see our method, TrioVecEvent, it outperforms the baseline method by large margins. And we can further look into the results. For example, comparing the performance of GeoBurst and GeoBurst Plus, we can see GeoBurst Plus is significantly better than the GeoBurst method. So this shows that the classification is indeed better than the top K for candidates filtering. And comparing the performance of GeoBurst Plus and our method, we can see our method has much bigger improvement than the GeoBurst Plus method. This is because the multimodal embeddings and the Bayesian mixture model can help us generate very quality geo-topic clusters as candidates. And also, after we extract the discriminative features, the candidate filtering step has very good performance as well. And in these slides, I show you some efficiency study of our method. We can go through them one by one. So for the first picture, I show you the convergence of the geo-topic clustering step. We use MFCMC to infer the parameters. You can see the clustering module converged within 10 iterations. And second is the embedding throughput. Because we use SGD to train the embedding, so this is actually showing the scalability of the training process. We can see the embedding module takes less time than the previous stream summarization-based method. And the third one is the time of online clustering. And we can see the time cost of the clustering step is a little bit larger than the previous method, but still acceptable. And the last one is the candidate filtering step based on the classification. Since this one just do a classification using a very small number of features, this one is very efficient. Okay, so to summarize, we have proposed a local event detection method based on multimodal embedding and discriminative candidate filtering. With the multimodal embeddings, we can find very coherent geo-topic clusters using a Bayesian mixture model. And we can also extract discriminative features for training accurate classifiers to select the true local events. There are several very interesting directions to explore as our future work. The first is that currently we only detect the events as a binary classification task. But in the future, it's interesting to come up with a method that can detect fine-grained local events, which means we can detect different types of events, whether protest or sports game. We can divide them into different categories. And second one is that we want to explore the evolving patterns for the same local events. What are the patterns? What are the things people talk about before the event happens? And what are the things during the event and after the event? So how can we mine the evolving patterns for during different stages of the same local events? That's also an interesting direction to go. And finally, we want to find more structured summarization of the event. We want to extract a structured schema for the event and also different attributes for the event. So that concludes my talk. Thank you, and I'd like to take questions.
Okay, thank you. Thank you very much.